let's start the next talk by Sibylle Möhle on propositional model counting and enumeration and automated model building in predicate logic. Thank you very much.
Thank you. So I chose this topic because I'm quite new in this community, and there is some connection if you want, and I need to show you a bit what I did in my earlier research life, let's say, because I'm interested in model representation mostly. And well, especially I was working in model propositional model enumeration, propositional model counting, because they also have many interesting applications. For example, here we can see enumeration. We use this in SMT, in weighted model integration, where you need the models because you want to execute operations on them, you want to integrate them. Then in model checking, free image commutation, and in circuit design also. There are also applications, of course, in predicate abstraction. So when it comes to model counting, a classical application, of course, is probabilistic reasoning. And I'm talking about exact model counting here, as opposed to this approximate model counting, which is, there's a lot of work on approximate model counting recently, not that much in exact model counting. So it also has applications in planning, cryptography, in Bayesian networks, further configuration, verification also. And then I did, after my PhD, I did a change towards first order logic. And in my PhD on model counting enumeration, I noticed that, of course, it's important how these models look like, how they are represented, especially, for example, in circuit design. And then I got interested also in knowing about model building in first order logic. So there is this, there's a lot of research also collected in a book called Automated Model Building. The idea is to find model representation formalisms to express models, because you can describe them, of course, in different ways. So, but let's start with counting and enumeration and propositional models first. Now, I guess this might be a bit basic. I have a formula. I have n different variables, of course. Now, in propositional logic, we know we have a propositional formula over n variables. So we know we have 2 to the power of n assignments. It's quite infeasible to just check all of them. Okay, just we want time out. So what can we do now? We want to restrict the work we need to execute. So one way is, and this was the classical way introduced here in 2000. We have a formula F. In this case, we have 2 clauses with over variables A and B and C and D. The variables occurring in F are, of course, A, B, C, and D, but now we see that these 2 here are disconnected somehow. So we can partition this formula into 2 clauses, or if we have a larger one, we could partition this formula into different clause sets, the set of variables of which are pairwise disjunct. Then what we can do is here we compute the number of clauses, number of models of the first clause or the first clause set. We compute the number of models of the second clause set, and we just multiply them. So what do we gain instead of checking? Now it's a bit. Instead of checking 16 possible assignments, we check twice, just 4. Okay. So now, well, if we have a large formula, this makes sense, of course, and we gain a lot. So it's cool because we reduce work in individual computations. Okay. But well, the classical way in INSAT, as a standard way, we have CDCL solvers and they are so powerful. Why not use them for counting? Okay, so we can say, well, we just throw CDCL, a CDCL-based SAT solver, and tell it to enumerate or count our models. But what happens now? Now we have this example here. We have F equal or not A or B, and C or D, and C or not D. Ignore the C for now. Here I have the execution tray, so I decide A, which means I assign A to true, which then lets me propagate B, because if A is true, of course, B needs false. If A is true, B needs to be true as well. So I indicate this by a vertical line because it's propagation reinforced. And then I can say, well, I guess C true, and I find the first model ABC. Okay, this is nice. Now, well, this is one model, but I need to check all assignments. So I go back and I take the last decision here, the most recent decision, and just flip it. So instead of assigning C to false, to true, now I assign it to false. And if C is false, I see, well, not D has to be false as well. But then I have an issue here because this clause becomes true, but this clause here becomes false. So I have a conflict, as we call it. Now, in CDCL, when we have a conflict, it can be that we have many decisions beforehand. So we don't want just to undo the most recent one, but maybe we can learn something. Maybe the error happened a long time ago. So we can use we call it conflict analysis to learn a clause which tells us what has gone wrong somehow. So this is a high-level talk. I do not go into details. My idea is also to give you an idea of what is around, rather than how it works. But we can talk about how it works, of course, offline always. So in this case, we would learn. So we would find C. C should have been set to true. So we learn like a clause. We derive a clause which contains only the variable C. Learn means we add it to the formula. Because of course, if we know now, C should have been set to true from the beginning because it cannot be false. So we can as well add it to the formula. Notice the C is implied by the formula. So I could also, of course, delete it anytime if the formula gets too big. But yeah. In this case, you would say, well, we had C, so we need to set C to true. And then we again guess when not A is true. Yeah, we get the model. When we get the model, we cannot learn anything. We just need to flip the most recent decision. And in the end, we find the third model, CAB. But now, well, there's a problem, right? Because now I have found the same model twice. If I want to count models, I would get the wrong count here. If I want to enumerate contradicting models, I get an error as well. In cases where I don't care, this would be fine. But here I'm talking about counting, or if I talk about enumeration, for me, it's about enumeration models which non-redundant, which don't enumerate models multiple times. So I have a problem in this case. So how can I solve this? There are two methods. Either I can add so-called blocking clauses. This is was done in propositional model enumeration only. Why? Because counting was mostly done with this component-based approach I showed before. And it consists in remembering somehow, I have found this model ABC, okay? Now, if I just add its negation to the formula, then I never will find ABC again, because whenever I have ABC set to false, to true, the formula will, this clause will get false, and I will get a conflict. But even more, what is interesting, I need not add not A or not B or not C. I only need to add a clause consisting of the negations of the decision literals. So the literals which I assigned the models, or we say also guessed a value, not assign the model, but assign the value by guessing. So in this case, this would be A and C. So if I add now not A or not C, what happens? So in this case, we just go back. Because we have found a model, we flip the most recent decision. We have the same, find the same conflict as before, but now when we are here, at this point, we have not A or not C. And we learn C. from conflict analysis. So now I know C needs to be true because I have this clause here. I just set A to false and I'm done. So I found models and they are non-redundant, so I'm happy. Okay. And what is the advantage here is we can learn from conflict, but of course now, while the learned clauses are redundant, these blocking clauses are not. So if we have many models, our formula just gets huge and things get slow because we are lost in unit propagation. So yeah, this one. Then what could we do? Well, we could instead, but it's very basic. It's like in the PLS style. We just always vector chronological. We just always flip the most recent decision, which obviously is not convenient. Because if we find a conflict here, for example, we have set A to true, B to true, C to false, and then we find a conflict. When we propagate D as before, then we just flip C as before, the same. But then the most recent decision to be flipped is A. And then now instead of learning C like before, we flip A. We set A to false. And now, we keep on setting C to false at some time. At some point, which doesn't make sense because we know it should be true. So now comes the nice part. Well, now this is the bad part. So we still have no formula blow-up, we find no redundant models, but we cannot learn from conflict. So we do a lot of work which is just unnecessary. The solution to that was, now, this is I have no graph here, why? This is the combination of CDCL with chronological backtracking. So the idea is the following. If we find, here we execute CDCL's conflict-driven close learning. So from the conflict we also learn to which point we can jump back. So go back over more than one decision level and continue from there. But now the point is that very often it has been seen that very often that assignments are just repeated. So the idea was around since a long time, but why could we not just backtrack chronologically? And finally in 2018 here, a solution was proposed which works like this. So at a certain point, we have a conflict. We learn this clause. We know we can go back to a certain decision level, which is much earlier, but we do not go back to the decision level. We just backtrack chronologically, just backtrack one decision level, but we will remember the clause here, we would add C in this case, has not the most recent decision level -1, but the decision level to which we would have backtracked if we would have applied CDCL. But there's a lot of stuff going around, but this is the main idea. So what we end up is that in the end on this trail, so this assignment we get. I mean, we assign every literal with a decision level. So if we do one decision on the decision level 1, here we only propagate. So B has decision level 1 and so on. So we have a mix of decision levels, and we need to take care of this. So we go on as long as it works, But then, of course, it might happen that we get conflicts at a lower decision level, and then we really go back. Only then. So, well, Widow's a bit hard to design, but I have also more slides and details if there's still time, which I'm not sure of. So now we find no redundant models. We need not to add any clauses here. We know blocking clauses, and we can learn from conflict. So this is really great. And now my idea was, okay, I formalized this chronological CDCL because I was interested in using it for counting. My topic was in counting. So my idea was, well, we have a formula here. I want to use CDC for counting with chronological backtracking. Let's see what comes out. Now, the point was here, I have some example formula here, not P or Q and P or Q. Quite simple one, right? I say, well, I have, for this example, I have 3 variables occurring in F. F is defined over, okay, R doesn't occur, but it's for showing, for illustration purposes, for not to making, to keep the example small. If I work this way, and then every model I get, I just output and conjoin disjoin with disjunction. So I find models RQ, not RPQ, not R, not PQ. So these are our assignments, satisfying assignments, right? These are like conjunctions of literals, yeah, which we call cubes. So if I can now use a disjunction to combine them, I get a DNF, of course, and the models of a DNF are all is this conjunct, so cubes, of course, here. So this M is logically equivalent to F, but more, we can see that in this case, all these clauses are pairwise contradicting. So this here contradicts with this one here because I have R and not R, the same here. Now, this clause here contradicts also with the last one because of this P and not P. So what is nice, I can just compute the number of models for each of these clauses and then sum them up. So here I see I have 2 variables out of 3. One is undefined, so this here represents 2 models. This is 1 and this is 1, so I get 4. In generally speaking, what I get is like disjunction of clauses, which are pairwise contradicting, and the sum of the model counts of which equivalents the model count of the formula. Of course, M is not unique because depending on how I choose variables when deciding and so on. But what was interesting here is that this kind of formula, this disjoint sum of products, is quite important in circuit design. I found a lot of work on this DSOP minimization. So keeping the DSOP, because then the circuit is also small. And many often they started from, maybe from CNF, I'm not sure. In this sense here, I would say I can translate the CNF formula into a DSOP formula. So this was interesting. And well, now, if I think this is like translation, but it's also like some knowledge compilation. So maybe you know the field of knowledge compilation or have heard of it. Is like here. Yeah. So you have a formula and you want to execute some tasks on it. Maybe you have a CNF you want to count. My counting now is a bit difficult on CNF. So how can I translate it such that I can count more efficiently? I could, for example, translate it to DSOP. Now we say that doesn't make sense because I mean, complexity-wise it's the same. So it could count directly. You're right. And usually this is used for cases where you want to execute not only one but multiple tasks. But of course, just by compilation, the program doesn't shrink, become smaller. Because otherwise, yeah, it'd be nice. It would win an award, I guess. And so you have the CNF form, which poses much as many problems. So, but it's still used very often to encode some problems, problems from real applications. And now you are the AI expert, and people come to you. I have this problem. Please present an encoding. You say, yeah, cool. I have a CNF now. Here you go. And then your clients, your colleagues are not happy because they want to execute some operations on them, right? And these operations are are quite intense on CNF. So you say, well, I found another form, another language, which supports these operations in polynomial time. Now, in knowledge compilation, in propositional logic, the form which is one of the important languages is this DDNNF, which is this deterministic decomposition negation normal form. So, like this one, the composable negation normal form, right? So you have these negations only in front of variables, and you have also that for all conjunctions do not share variables, which remembers us the component-based approach for model counting, right? So, where we could just partition the formula into subformula with pairwise disjoint variable sets. And then these junctions are pairwise contradicting, which remembers us how this up counting. But this is one of the, and this is not the only language, but it's one language which is used in knowledge compilation. And some references, I guess, yes. Yeah, no, they are coming. Okay, just to illustrate the main idea. So if I have a formula with a conjunction with pairwise disjoint variable sets, I can multiply the model counts. If I have disjunctions which are pairwise contradicting, I can sum up the model counts. This is just for illustrate a bit how this subformula, the DNN formula, how we can count the models of this DNN. In a certain sense, we can kind of rid of just the model count. So, yeah, this is in effect it's the same here. So now, knowledge compilation in general means we take some formula, usually it's CNF because maybe CNF is important in propositional logic. I also found work on knowledge compilation in first order logic. Didn't go into it. And yeah, we want to translate it into another language. And I really am missing this because this field of knowledge compilation was already prominent in, I think it was in the 80s. Marco Cadoli and others, they have done some quite work on it. And recently also done in the 2000s, Anand Darwish and Pierre Marquis have done lots of work in this in this era. And there are also some other languages over other languages come. So at this point, I was changing topic somehow, and I was switching to first order logic. And when I now look at automated model building, I want to represent something conveniently here. And the same holds for knowledge compilation. So this is where I see the connection somehow. And here are also the references for knowledge compilation. And well, now, if we seek for a representation of a model. Now, why? What do we want to do with this model? I mean, otherwise it doesn't make sense. So we want to be able to, given a model representation, we call it a model representation formalism. It's like a language in which I represent the models. This model. I want to be able to check, given an atom, whether this model, this representation is a model of this atom. Okay, and we want to do this fast. Fast means in polynomial time. Of course, we also want that whenever I have a representation, each representation specifies one single interpretation. Now we are in first order logic where we have this vocabulary sigma. And yeah. Now an interesting project task is I have a formula and I have this model. Does this model satisfy this formula? And I have two models, two model representations. Do they represent the same model? We want to be able to do these tasks too, but this is interesting because nothing is said about efficiency. So it's just enough to know. These are like these postulates which were defined by Möhle and Peltier, also yeah, mostly by them too. And what I was doing, what we are doing also, where I was in my further position, was we want to apply this somehow to represent models of first order clause sets. So we have the signature just to make sure we are on the same page with the basics. We have the signatures with formulas for function symbols and predicate symbols. We have, of course, terms which can contain variables. We have quantums without variables. Atoms are represented by capital letters, which the predicates are represented by capital letters. So we have atoms, and we have literals, which is atoms or negations and clauses like before somehow. And we also need some substitution and unification. We need this by if we have a set of first order clauses and we want to know whether this is satisfiable, one way we could do it is by an adaptation of CDCL for first order logic. It works quite similarly. We also have some kind of conflict clause learning, and the point here is that, of course, now here we cannot just propagate variables because, well, we have this maybe literals with variables, but then we use unification. So in this case, if we have some clause, uniclause P of A, then we have clause not P of X and or P of F of X. F is a function variable, X is a variable. So we say, well, first I know P of A needs to be true, okay? So I can build a trail like in propositional logic. And then I say, okay, if I apply this substitution here, I map X to A, then I can resolve these two. Well, it's resolution or unipropagation, however you want to call it. We know, okay, then if we have not P of, and we resolve these two, where X is replaced by F, then by A, then I know I have to put this P of F and so on. And now, okay, we say, well, this is our model. It's P of A, P of F of A, and so on, and it continues infinitely. But now there comes the problem. And also the major point I forgot to mention, in automated model building, the idea is to represent potentially infinite models in a finite manner, of course, because you cannot work with infinite structures. So in this case, you could say, well, but I could represent it just by P of X. This is a very simple, stupid example. And yeah, so in automated model building, there are many different kinds of model representation formalisms. Now, in our case, we chose to represent models of such clause by this set of literals. We bounded the literals in order to finish sooner or later, not to finish, to work forever. And what do we get out as a model representation formalism? We chose atoms. We chose just to represent this model by a set of atoms. There are other possibilities, but this is the one we were working on. So for this case, we found we can represent the models of these classes here by these three atoms. So we have P, X1, X3, and Y1, and so on are variables. And F and G are the function symbols occurring here. I forgot to write them. I am here. We have them. Now I'm running out of time, so I can show this offline how it is done. What I want to show you mostly is some context. Where does this somehow not fit together, but well. So my idea was to do model maybe I should start with them. What I'm currently working on is I want to represent and compute solutions of algebraic data types, maybe with additional theories, using CHC solvers. So my original idea was I have CHCs over algebraic data types, but of course I'm interested also in solving ADTs without CHCs. For example, one interesting thing which is also currently worked on by other groups is enriching the theories of algebraic data types with catamorphisms. So catamorphisms are these functions you execute on these recursive structures. Okay. So this was is what I'm interested in, and my part is explicitly in how to represent these solutions. Can I find a more appropriate representation formulas such that I can continue working with them? And of course, I need also procedures to compute those solutions, but also compute them in this form, which I need. The idea is a bit motivated also, so I want to combine this model representation stuff from first order logic, which was which came out of in a general, more general of first order logic general, in general, not from a particular community somehow. And yes, I guess it's it from my part. This was all this propositional models stuff. I mean, yeah, somehow like my travel from counting over models to models again. Okay, thank you.
We have time. We have almost 15 minutes.
Ah, yeah, yes, you're right. So,
if you want to go into details.
I don't know. I can show you. I know it's not much relevant for this community. Maybe I could show you how this is computed. I also have some to show you how I computed or chronological CDCL. Chronological CDCL. I knew it. It's interesting because my topic is counting, but I guess this is the paper with the most citations. Okay. I cannot take credit for the algorithm, so just for the formalization, okay? So the idea is the following. This is a real example I created for our paper in 2019. We have a large formula with, I think it was over 40 clauses. And now variables are just, as usual in such solvers, represented by integers. So we have here tau, the position. So this is position 4, 5, 6, 7. I omitted the first 3 for space, same space. I is this, now it's unfortunate, sometimes it's called interpretation, but in the end it's a trail. The trail is like a sequence of literals. So we have here in position 4, we have this, we have the variable 4, which is true, variable 5, which is true, 30, and so on. And here 7 is set to false, for example, indicated by a negative number. Delta is the decision level. So here, at this point, we are at decision level 3. So we had already 2 variables decided before. That's now don't matter for this here. So now here we have decision level 4. So we decided 5. So we guess we just set 5 to 2. We could also set to 4. In such solvers, usually you have some kind of decision strategy, which you follow according to the sum, which is also the reason for which maybe this DSOP is not unique. So, okay, what we see here now, of course, we have the decision levels of the literals on the trail is always increasing, right? That makes sense. So, yeah, some terminology. So we call these decision literals, which were decided. So, and we increased the level by 1. We also talk of blocks, as in SAT. So a block ranges from the first literal in a decision level to the last literal before the next decision level. Okay, here, so we have this block at level 4. We also now have introduced the notion of slice. In this case, it's the same. Slice is composed of all the literals, the same decision level. So here we have slice at decision level 4 of this trail I. Good. And if we say, well, we also have this trail defined, the trail at decision containing literals at most at decision level 4, which is all before until decision level 4 is finished. In this case, it's white. Now what happens here? We had a conflict. And we had this clause here, -47, -17, -44, which is falsified because the variables were all set to true. And what we see here, we have decision level 6 currently. So we call this conflict level 6. Good. We apply conflict analysis and say, oh, we learn this clause here. Let's see. We add this clause here together to the formula. And now when in conflict analysis, how do we decide to which level we jump back? So every of these literals, of course, has its decision level here. And we jump back to the second highest decision level in the conflict. Some people call it conflict clause. I prefer call it conflict learned clause. Why? Because if we jump back at a certain point, we can propagate the literal with the highest decision level in the clause. Okay, so this will keep their values, and 23 will just be unassigned. So the jump level, so the level to which we would go back is 4, because the second highest level here is 4. So after backtrack, yes, we would have to jump here. But now we are in chronological CDCL. We say, well, we go back to decision level 5. We just go back 1. Okay, so then it looks like this. I should have, yes, 13. We have here still our 30, 47, 18, which were all set to false, and 23 doesn't occur anymore. Okay, it doesn't occur anymore, but well, we can propagate it because it needs to become true, because otherwise this clause we just learned would become false, right? But now, if we see, we would have jumped back here. And if we then would propagate 23, it would get decision level 4, right? Because it gets the highest level in the clause. In CDCL, it would be the current decision level. CDCL, the current decision level would be 4, so we would assign it decision level 4. But now we are just back to 5, but we want to remember, we should, well, really this 23 should be a decision level 4, okay? And now comes the point, now we have this out of order literal here on the trail. It doesn't harm much. I mean, for implementation purposes, one could also decide to just move to reorder the trail at this point, but I didn't want to do this for this work. And yeah, what we see now, if you have this out of order literal, if you go for blocks, the definition of block is clear. The first literal from the new decision level until the last before the next one. The next one is here. So this is still a block. But for the slice, which contains all literals of the same decision level, 4 in this case, we have this 5 here, and this one here. So, yeah. And where is this important? We now just continue. We were here before, we did all these assignments. We had some other out of order literals, but what I wanted to find here, there's a special case in this chronological backtracking. which I wanted to highlight. So if at this point now we have conflict, the conflicting clause, or the clause which becomes false is this one here, 17 minus 42 minus 12. So I need to see the time now. Then now we need to execute conflict analysis. We see here. Let's see. Yes. Conflicting clauses here for 5. So we first backtrack to the conflict. Now why is 4 and not 5? I'm not sure anymore. So, yes, now it's 5. But this, no, I'm not, because I have to check. I'm sure it's correct, but I now need to check why we don't jump back to the conflict level, because the conflict level here would be fine. But why we backtrack to level 4? This I did always see. I can check, and I will. You can ask them to me. Okay. Because the idea is we can either execute conflict analysis now, and then determine the level to which we need to backtrack, or we can first backtrack to the conflict level and then do conflict analysis. Maybe this was the case, yes. And the result is the same. You can draw it and we will see it's the same. In this case, we need to backtrack to decision level 4, which means that now, if we go back to decision level 4, we need to maintain the slices 1 to 4. Okay. We need to discard all slices of decision level higher than 4. So we keep this one. We keep this one and this one, and this, and of course the ones before. So, and this is the difference. I wanted to show also that what can happen also is that usually when you have yeah, now I know what was the point. So usually in CDCL, in the conflicting clause, you have at least 2 literals the same decision level, right? Because otherwise there's something wrong. I mean, you could have, if you had not, then in this clause you would have 1 literal which could be propagated. So, and with the chronological CDCL, it can happen that you have a conflicting clause with only one literal at decision at conflict level, with a single one. Yes, this was it. Yeah, this was what I wanted to show. So yeah, I guess I'm now definitely out of time. Right?
No, you are still fine, but we can have another question if anyone.
I can show you more. I think this was the most relevant, maybe also for.
Any other question?
Yeah, I have a question. Can you go please to the slide with the rules, I think it was around 9-10, slide 9-10.
Show the rules, right?
Before, yeah, here. So here, here the rules are, I think there is a typo because there is no R in F, right?
Yeah, or, this is made up a bit.
Okay.
I know usually you don't do this, but I did it just for show. I wanted to keep the example small. As soon as I had some R in F, then M was becoming quite large, and this I didn't want.
But then what kind of rules did you apply to get this M?
That's my notebook. Okay, so the idea is you do unit propagation and decisions as in SAT, as in CDCL. Then whenever you get a conflict, you backtrack chronologically, but still learn the clause like before. I can show you the rules. I have them on my notebook because usually I show them just for making impression, but it's complete. It's a logical framework. There's no implementation.
I see.
Yeah. It is exactly this. So you do everything like in CDCL. When you learn, when you find a model, you backtrack one decision.
Yeah, I'm familiar with CDCL, but I don't know how you get an R, an additional 8.
No, this is just, I say, well, the formula F is defined over P, Q, and R. And in my experience, how shall I say? I could have made a formula F where R also occurs, but then M became so large and I wanted a real example.
Okay.
So it's just, usually you talk of variables occurring in F, and I could say, well, I define a formula over a set of variables, but one variable might not occur. So its value is just irrelevant. So for example, But of course, if you say you have this P, Q, and R, when you do decisions and you need to decide R at a certain point, because the SAT solver knows to have found the model only when all variables are assigned and no conflict occurs.
Yeah.
And so you need to assign R at a certain point. That's a bit made up.
If you just add R or not R in the F on the left side, top left side.
I have to check.
So
yes.
it makes it's irrelevant and it could still satisfy.
But I will try that out.
Yeah, okay.
Okay, and the model counting is easier for disjunctive normal form than for conjunctive because you could use straight-in encoding and.
No, it's not, because in DNF you could have cubes which share models.
Okay. And bringing.
Otherwise, P would be equal to NP, I guess. I mean, no, maybe not, but sharp P would be equal to something else. The point here is that you can sum up the model counts only if the models represented. Here, a representation of this formula would be A and B and C, or C and not A, or C and A or B. Then you would count this by 1, this by 1. This would be 2, which would get you the wrong model count. Now these are equal, but you could also maybe find them if you have something like you have ABC in your formula, then you have a model AB and you have a model BC. Both represent also the model ABC. So ABC would be counted twice. This is an easier example. There is a paper on the hardness of sharp DNF. So,
I was wondering, so you mentioned solvability of first order satisfiability. What is your notion of solvability here?
deciding whether there's a
I believe, if I'm not misremembering,
should be satisfiability, otherwise I was wrong.
So satisfiability of first order logic is not decidable. So I'm curious what you mean by solvability then. Solving the satisfiability problem first order.
Yeah, solving for me is finding a model.
Okay, so it's a semi-decidable. So having a possibly a non-terminating run is fine.
I guess maybe the word was not quite. Yeah. For me.
No, I mean there's also a different notion of solvability, but that's why I'm wondering what notion are you using. So are you also trying to find in a proof system of the model theory counterexample at the same time while you're searching for? So
this would be ideal. I mean, in this case, we want to represent a specific model. This needs to be pointed out. So what model building is about specifying a specific. expressing a specific model, and in this case here, I want just to represent the model. Of course, it could be also a counting model like this. Maybe there's some more convenient way depending on what you want to do with this model afterwards.
But okay.
Yeah.
Maybe yeah.
Yeah, maybe this was also a bit a naive idea, but this was what came to my mind first, and yeah.
So, but I mean, in first order logic, there are some unsolvable problems. So then, if you would then search for a proof or search for a model, you won't find either.
Yeah.
And this is the famous incompleteness result of Gödel. So
Yeah.
I mean, if that was why I was wondering what you mean by solvability here.
Yeah, maybe it was a bit unfortunate. So the idea is maybe if you have some like this formula and you have a model and you want to work with this model, typically these are infinite mostly, as soon as you have function symbols, but then you cannot work with this maybe, but if you can represent them in a finite manner, this can be like in this case here with atoms, with variables. But there are also other representation formalisms. There are, for example, constrained atoms and all these kind of things. There's a lot of work. There are things like somehow describing the model. Somehow, yeah. My question was, can we use this somehow? There must have maybe, yeah. I'm maybe new and naive to this. Yeah. This is some kind of vision. Okay.
Let's say Sibylle again.